All right, next we're going to move to looking at a more complicated example. This is one where you have a chain rule within a chain rule. You actually do the chain rule twice. So how would I find this derivative? Well, this is the same thing as the derivative of e raised to the sine of x cubed. So what's going on here is I'm taking the derivative. I've got an exponential function, and then in that exponent I've got the sine function, and that function is cubed. So I need to sort of peel back the layers and figure out sort of which function is my outermost function, etc., in terms of evaluating this. And the way to think about this is, if you were to calculate this by hand, you would first plug in the value for x, you would take the sine of that, and then after that you would cube it, and then once you had that expression, you would do e to that power. So that means your innermost calculation is the sine, that next one outer is the cubed, and then your outermost is the e. So we want to break it into those three pieces, and I'm going to use the Leibniz notation for this. So I'm going to say y is equal to e to the u. My u is equal to sine of x cubed, which I'm now going to call that sine of x a different variable. We'll call it v. And my v is equal to sine of x. Okay, so v is my innermost function, and then I'm cubing that, and then after I cube that, that's u is equal to v cubed. I plug that in up here, and I get the whole expression. And I can take some derivatives here. dy du equals e to the u. du dv is equal to 3v squared, and dv dx is equal to cosine x. So the chain rule by Leibniz would say dy over dx, you're going to go piece by piece, dy over du times du over dv times dv over dx. And notice, I didn't mention this before, but you can think of this, it's almost like this du cancels with that du, and that dv cancels with that dv, so you're just left with dy over dx. That's why the Leibniz notation is sort of nice, because it sort of makes sense. In any case, I can now plug these in. That's e to the u times 3v squared times cosine x. But as I said before, I want everything to be in terms of x, not in terms of u and v. So e to the u, my u is sine of x cubed, so I can write sine cubed x for my u. My v is equal to sine of x, so this becomes a 3 sine squared of x, and then the cosine x is just cosine x. And that's my answer. If I wanted to do it the fast way, and this is the way you're really going to want to think about it, I would do d dx of e to the sine of x cubed is equal to, I would say, well, my outer function is e to something, and when I take the derivative of e to the x, I just get back e to the x. So I'm going to leave that just like it is. And then I have to chain rule by taking the derivative of this function. But sine x cubed is a composite function, and the outer function is the 3. So I bring the 3 down, I keep the sine x the same, and then I square that, because I'm subtracting 1 from the exponent, times, and now I take the derivative of that thing, and I get cosine x. So that's the same answer, but I did it with basically none of this extra work shown in machinery. And this is what I expect to see at the end of the day. Okay. Go ahead and pause the video now and work on exercise 3 on your own. Okay, so exercise 3, there's actually 2 different ways of doing this. So this is the same thing as d dx of e to the x raised to the 1/3 power. And I can use the chain rule on it like this, or I can make a slight modification. So when I take the derivative of e to the x to the 1/3 power, I think to myself, well, my outer function is this thing to the 1/3 power, So when I take the derivative of that, the 1/3 comes down. My stuff on the inside of the parentheses stays the same. And then I subtract 1 from the exponent. 1/3 minus 1 is -2/3. And then I chain rule and I take the derivative of e to the x, and I get another e to the x out here. And I can actually simplify this a little bit. So this is a 1/3 e to the x. I can multiply, because these exponents are separated by parentheses, I can multiply that in, and this is a -2x over 3 times e to the x. And if I have the same base, I can add the exponents. So this becomes a 1/3 e to the x minus 2x over 3. That's a -2/3 x, really is maybe a better way of thinking about it. So x minus 2/3 x is just 1/3 x. And that's my answer. Now another way of doing it is to think d dx of e to the x raised to the 1/3 power. These are separated by a parentheses. Exponents separated by a parentheses can be multiplied together to give you e to the 1/3 x. Or maybe we should write it as e to the x over 3. So what's going on here now is I still have a composite function. My outer function is e and my inner function is x, x over 3. Which maybe I'll actually write as 1/3 times x. Might be a little easier to tell what's going on. So when I take the derivative of this, my outer function is e to something. When you take the derivative of an e function, you just get back what you started out with. And now I need to chain rule by taking the derivative of the 1/3 x, and the 1/3 will just go, that's a constant out in front, so we don't touch it, and the derivative of x is just 1, so I multiply that by 1/3, and I get 1/3 e to the x over 3, which is the same thing I got over here, and I'm done.